All right, welcome to Chapter 5, Unit 5. We are talking about exponents, polynomials, and polynomial functions in Chapter 5. We're stepping away from matrices and systems, so a couple of you can breathe deep. A couple of you might be a little disappointed. But we're going to go, so basically we're going to step away from those linears and we're going to get into the higher power equations, those quadratics and the cubics and the things like that. But before we do that, we have to talk about the exponents that go with that. So today's section 5.1, integers and integer exponents, and scientific notation. If you'll recall, you had a worksheet on some of these rules and combining exponents. That's kind of the theme for today. But before we get there, let's remind ourselves exactly what happens in an exponential expression. So an exponential expression is obviously, it doesn't have an equal sign, right? Expression is just a combination of some factors and stuff. And this one happens to have an exponent in it, hence exponential expression. Looks something like this: 2 to the 5th, right? Or 4 to the 8th, 6 to the 9th, 3 to the negative 4th, x squared, things like that, right? Where, and what this means, 2 to the 5th, it means it's being multiplied by itself 5 times. It does not mean 2 times 5. 2 to the 5th does not mean 2 times 5, right? That definitely is not the same thing. What it does mean is that you have 2 times 2 times 2 times 2 times 2, right? It's repeated a whole bunch of times, the 5 times. And then we get a result, when you actually do that, results in 32. Recall that 2 is called the base. The big number on the bottom here is called the base. Can maybe write that in pink. This is the base, whereas the 5 up here, that's the part we call the exponent. A lot of people remember the exponent part, not a lot of people remember the base part, so make sure you know both parts of that. And then if we call 32 the solution, right? So 5, the base of 2 to the exponent of 5 is equal to the solution of 32. Alrighty. Now let's dive into those rules. So when you have stuff like this, you have multiple ones of these, just like when combining like terms, or combining, x's or 2 plus 2, right? We can combine these guys as well, but there's a few tricks we get to follow, kind of make our life easier. The first one is called the product rule. We also have the zero exponent rule, the negative exponent rule, the quotient rule, the power of a power rule, and the distribution rule. And all of these have to deal with exponents. You can see some examples right here. This table is for you for when you're doing homework, studying for your tests. It's got when to use, how to use it, examples, and be careful of what not to do. This last one is mistakes, so don't take this as what you should do, right? These are the mistakes people make, so watch out for that. How to use them is right over here. Instead of just reading this table, though, because that's incredibly boring and nobody wants to do that, we're going to actually head down to example 1.1 and just start using these rules individually. That way we can get an overview here. But if at any point you maybe are doing your homework or you forget something, you can always refer back to the table up above. Alright, so example 1.1, using the product rule to simplify these following expressions. None of these expressions have equal signs, right? So we're not ever going to get that we equal a number. Now with the numbers, when it's all numbers and no variables, yes, you can actually solve it out, right? And we probably will. But we're not going to simplify it all the way down to a single real number. We just want to see how these rules work. So if you want to, you can keep simplifying it. But I'm going to kind of stop where it is the most simplified expression. In other words, I'm going to stop where we get to something like this, 2 to the 5th. Alright, so let's try out this first one. What does the product rule say? Well, if we have something like 3 to the 4th times 3 to the 7th, well, notice that we have the same base. Product rule says you must have the same base for this to work. So we'll start with same base. This here is a base of 3, right? And if that's the case, if you have the same base and it's being raised to a whole bunch of powers, then you can think of it this way. I have 3 to the 4th, which is 3 times 3 times 3 times 3, right? And then that is being multiplied. It's being multiplied by another 7 3's, right? 3 to the 7th would be 3 times 3 times 3 times 3 times 3 times 3 times 3. Wow, that's a lot of 3's. So we've got this sort of situation going on here. We have 4 pink 3's and 7 blue 3's. Now, just because I've written them in 2 different colors doesn't mean they're different types of 3's, right? It's all a whole bunch of 3's being multiplied together. So the product rule says if you have a an exponent of one base and an exponent of another base, the same base and two different exponents, then you can essentially combine them into one big exponent. And let's see how many 3's we actually have now. We have 4 plus 7 is 11. So this would be a new 3 to the 11th. Now that's just sort of how it works, but there's a shortcut, right? So because it works this way, because that's actually what we're saying, we can kind of take a shortcut. If we notice that we have two of the same base being multiplied, and that's very important, it's called the product rule because they're being multiplied, not added. But if they're being multiplied, then we can take a shortcut. We can say 3 to the 4th times 3 to the 7th is equal to the 3 to the 4th plus 7. Right? So we can add their exponents. For multiplying the bases, we can add their exponents. We arrive at that same answer, 3 to the 11th. And when we really think about it, that's what we did, right? We took 3 to the 4th, and we added the we took the 4 3's, we added the 7 3's, we got 3 to the 4 plus 7, or 3 to the 11th. Let's try it again with this guy right here. We have 5 to the 3rd times 5, or just a 5. What's the exponent on that 5 there? I encourage you to maybe pause the video and talk about what's the exponent there. Only for a few seconds, though. Alrighty, I hope you said that the exponent was 1. That's absolutely right. Remember, when there is no visible exponent, it is a power of 1, right? It's not a power of 0. So here, if we apply the product rule, we can see we have the same base, right? And they are being multiplied. If they weren't, we couldn't be able to do anything. We wouldn't be able to use this rule. But they are, so we can do 5 to the 3 plus 1. And we end up with an answer of 5 to the 4th. So this little expression here can be simplified to 5 to the 4th. Now again, from here you could go on and further simplify, right? 5 to the 4th would be 5 times itself 4 times, which would be 5 times 5 is 25, times 5 is 125, times 5 is 625. So technically you could simplify this one more and say 625, but this is kind of where the important information of this problem comes out, how to combine that to get 5 to the 4th. Alright, let's continue on to the next one. I don't know why I'm favoring this blue today. This one, now we have variables, but remember, a variable is just a number we don't know yet. So they follow all the same rules, right? Variables, big numbers, they don't change anything about the rules. They have to follow all the same thing. So all we have to do is check, do we have the same base? Looks like we do. They're all y's in this situation. Yes, there are 3 of them, but they're all being multiplied. So the product rule can be applied twice. We can start with these first two guys, and we can say, okay, y to the 3 plus 8 times y squared would be y to the 11th plus times y squared. And then we can do it again, and we can say y to the 11 plus 2, or a total of y to the 13th. In other words, we have 3 y's, 8 y's, and 2 y's, and they all come together to give us 13 y's. Now, what we just did here, this whole grouping the first two and then doing the last one, that's what we call the associative property. The associative property, right? Way back up here, you'll notice it is not in our exponent rule or our vocab that's in the next chapter, but that's okay. Just a little reminder about the associative property. It says you can combine them in any order. If you wanted to combine that 8 and 2 first, you could call it y to the 10th and add it to the 3. You'd still get y to the 13th, right? Or, you know, if you're good at handling all 3 at the same time, go for it. Handle all 3 at the same time. But the associative property lets you do that. Alright, last one for the product rule. We've got a couple things going on here. We've got 5y squared times minus 3y to the 4th. Notice again, everything's being multiplied. So I'm going to rewrite this just a little bit, where I kind of split up each guy. So I can double check that, in fact, yes, everything is still being multiplied. I'll even put parentheses around this guy so it shows that. Since everything is being multiplied, I can now use a slightly different property. It's called commutative, if you remember that way back when, and I can rearrange these guys. So I'm going to switch these two. I'm going to switch these two guys to do that. And I end up, whoops, y squared. I don't want to drop anything, I just want to switch them. And now I've got something that I can clearly combine, right? I've got some numbers that I can squish together. I can squish those together. I can actually multiply. 5 times negative 3 gives me negative 15. And then I can use the product rule on this second part here. The second part says y squared times y to the 4th, which is a total of y to the 6th. And that's how I can combine this last guy using the commutative property and the product rule, pardon me. So up here in this last problem, we can write this down. Associative And then what we just used over here was called the commutative. Think like community. You can switch everywhere in your community, right? These will come back time and time again when we're working with these a lot, so make sure you keep them in the back of your mind. But also remember the product rule. Product rule says you can, as long as you have the same base, you can add the exponents. Same base being multiplied. Alright, any questions on the product rule? Pause the video now, discuss them. Otherwise, we'll be moving on to the zero exponent rule. Okay, example 1.2, using the zero exponent rule to simplify the expression. So this rule is slightly different, right? It involves a zero in the exponent. I know, big shocker, right? So zero exponent rule says that when you have something to the zero power, anything to the zero power, it's equal to what? Anyone remember what it is equal to? Something to the zero power. Every single time it's equal to the same thing. Alright, I hope you said 1. It is not 0. 6 to the 0 does not equal 0, okay? People like to think it's super easy and they can just relate 0 and 0, right? That's not true. In fact, what it is it's equal to 1. It's equal to 1. Anything to the 0 power is equal to 1. Anything to the 0 power equals 1 every single time. The reason for that dives into some abstract algebra. There's a lengthy, extensive proof on it. If you'd like to see it, I'd be happy to send it to you. Or you can come in after school, you can go over it, you can come to math club, that'd be fun. But for now, just remember it as a fact. As a fact. It's pretty much decided that this is true so that all the other math we build on it will actually work. But that's the reason. So anything to the 0 power, anything, 6 to the 0 power is equal to 1, 5 to the 0 power is equal to 1, a million to the 0 power is equal to 1, x to the 0 power is equal to 1. No matter what it is, anything to the 0 power is equal to 1. Let's look at this next question, though. Let's see very specifically what are we talking about here. I'm not talking about negative 6 to the 0 power. Here I have negative of 6 to the 0 power. Watch out. When you're dealing with exponents, you may have to look very, very carefully about where your parentheses lie. Think about this for a sec. We had a problem similar to this in the last chapter where we were evaluating functions. Or sorry, maybe that was chapter 3, even way back when. But we had something very similar to this where a negative is not in the parentheses, right? And that was when you had something like this, it was like negative 2 squared versus negative 2 squared, right? And there was a difference between the two. If the negative was on the inside of the parentheses, that means you also square it, right? So it'd be negative 2 times negative 2, you get 4. Otherwise, the negative is not a part of that square part. So the first one simplifies to 4, then it is negated, right? So it's 2 times 2 simplifies to 4, and then you take the negative of that. So this one would be 4, and this one would simplify to negative 4. So there's a difference here. Knowing that, remembering that, let's look back at this again. So are we talking about negative 6 to the 0 power, or 0 power, or 6 to the 0 power and then negated? Which case do we have here? That's right, we have the first case, right, where the negative is not in parentheses. So we have to be careful when we simplify this guy. 6 to the 0, where we already talked about that, that's going to be a 1, right? And then we negate it to get that negative 1. So watch out for that. Those parentheses can really trip you up. All right. What about this last problem here? Well, it's not product rule, right? Because there's no multiplication, and they're not even the same base. I know it looks very similar to what we were doing back up here, but they're not the same base. They're being added. We have 5 to the 0 plus 12 to the 0. What is the solution to this problem? Go ahead and pause the video now and see if you can do it yourself. Only take about 5 seconds, though. Alrighty, so I hope you tried this. Remember, anything to the 0 power is 1. So 5 to the 0 is 1. 12 to the 0 is 1. Therefore, the solution is 1 plus 1, or 2. And that's pretty much what we have with the zero product property. Anytime you see anything to the 0 power, if you want to leave yourself a note that this works for exponents too, x to the 0 power is equal to 1. Anything to the 0 power is equal to 1. So as soon as you see that, you can kind of cancel it out. You can We'll see later on how that'll affect it when we have really big things we need to reduce, but this is a rule that people tend to like because it is so straightforward. Anything to the 0 power is 1. Alrighty, let's talk about the negative exponent rule. This one's a little bit trickier. It's another definition, another thing like the 0 power where it's because we say so. The negative exponent rule says that if you have something to the negative power, the definition of that, because the exponent is negative, it is the same thing as the reciprocal of the positive power. So a negative exponent you can change by using the reciprocal to a positive power. A lot of terminology there. So let's take a look at A and see how that would work. So 2 to the negative 3 would simplify. We can use the reciprocal to the positive power. So I get 1 over 2 to the 3rd, 1 over 2 to the positive 3rd, instead of 2 to the negative 3. Again, that's because that's the definition of a negative exponent. So anything to the negative 1, that becomes the reciprocal to the positive 1. Negative 54, reciprocal to the positive 54, right? That's only in the exponent. I'm not saying every single number that's negative is going to give you a reciprocal, but the negative 3 becomes a positive 3 on the bottom. And then if you want to, you can simplify this to 1 over 8. Absolutely correct. On the test, you probably want to simplify it down if you can, right? But for the demonstration purposes today, this is pretty much what this is what the negative exponent rule says. All right, let's try another one. Let's head down to, let's use green, B here. What does that one say? What would that one, we actually take a look at B and C together. We have again this parentheses issue going on here. So these are very, very similar. The only thing different is that parentheses, right? And that's going to change our answer to this problem. What does the parentheses around the first one in B say? What is it trying to tell you? Right, it's trying to tell you that the 5 is also being raised to the negative 3 power, right? So it's just kind of like the negative back in the 6th problem, right? So here, everything in B is being raised to the negative 3rd power. Therefore, everything will be reciprocated, right? To the 3rd power. So everything goes on the bottom. Everything in the parentheses goes on the bottom. And then, yes, we can simplify this. 1 over 125 z cubed, right? And we'll talk a little bit more about how that works in the distribution rule, but that is essentially the case. You've got this whole thing in the parentheses, so the whole thing goes to the bottom. Let's compare that now to C, where the 5 is not in the parentheses. In fact, there are no parentheses. So what does that mean? How is this going to differ? What do you think? Alright, so just like in 6, or just like in B of the last problem, we first do that the part that's right next to the exponent, and then we convert anything else if we had anything else. So because this 5 is not in parentheses, because the z is not in parentheses, then what that says is this negative 3 is only attached to that z, right? So in other words, it's 5 times z to the negative 3. And so let's do this in a different color so we know that these are 2 different examples. Let's use red. So 5 times z to the negative 3rd. And then I'll just convert the z to the negative 3rd part, right? So 5 times 1 over z to the 3rd, or if we put them together, 5 over z to the 3rd. Notice this time the z stays up top, or the 5 stays up top, right? The 5 will always stay in the numerator. In the last problem, it was being raised to a negative power, so it went into the denominator. And those are 2 very different answers, right? That's very different, depending on where those parentheses lie. Why don't you guys try out D and E? It's real fast. Pause the video, try it out, and because they are very, very similar to the problems we just did, and then we'll do them together in about 30 seconds. Okay, I hope you had a chance to actually pause and try these problems out. If you didn't, that's okay. So problem number D, that sounds funny, problem number D, section D is very similar to the one we just did in C, right? That parenthesis, that negative is not there, it's not included in the m. So this, just the m, is it's kind of like negative 1 times 1 over m to the negative 2, right? And therefore it's negative 1 over m squared, right? That would be our solution to this first one. Whereas in the second one, that negative is being included in that parentheses. So we would want to actually include that square. So we have 1 over negative m squared. And you may argue, of course, anything squared is going to be positive, so essentially this is the same thing as 1 over m squared, which you would be correct. But for this purposes, we wanted to take a look at the difference between this final red one and this first pink one here. So notice the negatives up top, negatives down low. And in the end, you can see it is a different answer, right? A negative 1 over m squared is different from a positive 1 over m squared. All right. Negative exponents work for numbers. Of course they do, right? We just saw that working up in problem 1, and so we can use them to when we're solving other problems, right? If we have 3 to the negative 1 plus 4 to the negative 1, we can convert both of these. That becomes a 1/3 plus a 1/4, right? Just switch it over. So 3 to the negative 1 becomes 1 over 3 to the positive 1, plus 4 to the negative first becomes plus 1 over 4 to the positive first, right? And then we can add these together. If I add these together, that would be, let's see, I need a common denominator of 12. Common denominator 12 is the first thing 3 and 4 have in common. In order for this first fraction to equal this first fraction, in order for this guy to equal that guy, I need to times everything by 4. So 4/12 and 1/3, same thing. Same thing over here. I need this guy to equal this guy, so 3/12. I end up getting 7/12. Cool. Alrighty, and the very last one for the negative exponent rule. If it's already a fraction, the rule still applies. Notice here it doesn't say make it a fraction. It says use the reciprocal. The reciprocal of a fraction is just going to be the flipped fraction, right? And if it happens to become a whole number, fabulous. But remember, reciprocal means you can flip it either way. You can take numerators to denominators, denominators to numerators. In fact, if you have both, something like 2/3, you should take both. Make it 3 halves, right? So make sure if it's already a fraction, the rule still works. In this case, if we had it on the bottom, that's going to flip to the top, and it's still going to become a positive. Or in other words, it's going to become 2 to the 3rd. Cool, so it works both ways. If you have any questions at all about the negative exponent rule, because it can get a little tricky about where those parentheses lie and what you should do with this, should it be positive, things like that, please pause the video now. Make sure you get those questions answered. All right, quotient rule. Quotient rule. We're halfway there. We've got 2 more. We're going to rope in distribution and power of a power there. So we've got 3 more technically, but we're going to talk about the quotient rule first. Quotient's the opposite of product, right? So quotient means divide, or it means those fractions. And I don't know if you noticed this, but a division symbol is a fraction. It's got something divided by something, right? So it's a fraction. So basically, we're dealing with those that look like fractions. Now the quotient rule says, again, you must have the same base. Must have the same base, otherwise this rule doesn't really work, and we're going to see why in a sec. If you have the same base, though, like you do in example A, you can essentially cancel some stuff. You can cancel some stuff. Some people view it as subtraction. We'll look at it both ways. But here's what's happening. If I have 3 to the 7th over 3 squared, well then what I have is 3 times 3 times 3 times 3 times 3 times 3 times 3 over 3 times 3, right? That's what I have. I have 7 3's on the top and 2 3's on the bottom. Now, for every 3 I have on the top, I can cancel it with a 3 on the bottom, because if we remember that 3 divided by 3 is just going to be 1. So every time I have a 3 divided by 3, that's going to cancel out to 1. I'm going to multiply by 3 and then divide by 3, right? They go away. So I'm going to cancel out every instance of that I have. What I'm left with is 5 3's on the top. 1, 2, 3, 4, 5. Since I have 5 3's on the top, my result will be 3 to the 5th. So that's the one way to think about it, the canceling way. The other way people think about it is, again, just a subtraction way. So just like with product rule, we strung them out, we added them together. Here, we're canceling them. And another way to think about it is taking the top value, so 3 to the 7th, and we're going to subtract the second that we took off, right? So we took off 2 because we ended up canceling 2. So 3 to the 7 minus 2 is 3 to the 5th. And you always subtract top to bottom. Always subtract numerator minus denominator. Sometimes, yes, you will end up with a negative number, but then you just apply the negative exponent rule, right? And then you've got 1 over whatever. But here you always subtract numerator minus denominator. I'm going to write that a little clearer. Numerator minus denominator. All right. Personally, I think when you're solving larger expressions, sometimes the cancel rule is just a way to think about it. Thinking about it in a canceling kind of way is sometimes a little more helpful. Other than subtracting, but whichever method you seem to like, totally fine. Let's do the same thing with a variable expression now. We've got p to the 6th over p squared. We can think of this as how many are going to cancel. Start with how many are going to cancel. If I've got 6 on the top and 2 on the bottom, well, I've got 1, 2, 3, 4, 5, 6 on the top and 2 on the bottom. And again, it looks like 2 cancel, right? 2 cancel, I'm left with p to the 4th. Now, if you can do that part in your head and you can say, okay, I've got 6 on the top, I've got 2 on the bottom, 2 are going to cancel, therefore it's p to the 4th, right? You can definitely do that in your head because sometimes you'll get something like p to the 72nd, and I really don't want you spending the entire period writing out 72 different p's, but essentially that's the process, right? How many can you cancel with the top and the bottom? In other words, we can say we have p to the 6th minus 2 or p to the 4th, right? The numerator minus the denominator. All right, let's do one more. Another variable expression. This time I've got more on the bottom than I do on the top, but that's okay. I never said anything about how many can you cancel from the numerator, right? Just said you have to subtract the numerator from the denominator. So let's take a look at this one in the canceling kind of way. So have 7 k's on the top. There's 4 of them. There's 3 more. Over, I got 12. 1, 2, 3, 4, 5, 6. See, this is one of those instances where I'm saying you've got a lot of k's. So you maybe, if you're able to do this in your head, would be a great thing, but that's okay. For now, we can just look at how many will cancel. So it looks like I've got one that'll cancel here, 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 and here. And what am I left with? I'm left with 5 k's on the bottom, right? I'm left with 5 k's on the bottom. So essentially, I'm not left with k to the 5th, right? Because this was all of these guys, both of these guys had them on the top, right? But in other words, if we looked back at this first one, we had 3 to the 5th over 1, right? And it was over 1. And then here we have p to the 4th over 1. Here we have 1 over k to the 5th. So this is 1 over k to the 5th. In other words, if you didn't want to take the time to write these all out, we could say, okay, k to the 7th minus 12, which is k to the negative 5th, and say, oh, hey, look, we can use that negative exponent rule to get the same thing that we just got, right? Because anything to the negative power is going to be 1 over anything to the positive power. So either way works. Again, I kind of like the canceling idea, especially if you have multiple things on the top and the bottom. We'll see that in a sec. But either the subtraction method or the canceling method works for the quotient rule. We're talking about what cancels in the quotient rule. The last rule we're going to be talking about, there's actually 2 rules here roped into here. The first one's called power of a power. And we will also be talking about the distribution rule. Distribution rule. Distribution rule ropes so nicely with power of a power that we just kind of lump them in the same section. So that's basically what's happening here. But let's talk about this first one right here. This one is the power of a power rule. So this is power of a power. And you can see that we have the power, we have p being raised to a power 8, being raised to another power 3. That's why it's called power of a power. So you've got multiple things going on here. Be very careful. This does not say p to the 8th times p to the 3rd, right? That's not what we're saying here. We're saying we have p to the 8th 3 times, right? So we have p to the 8th times p to the 8th times p to the 8th. That's what we're talking about here. 3 multiples of p to the 8th. Then we can combine those using the product rule, and we see that we get p to the 8 plus 8 plus 8, or we get p to the 24th. P to the 24th. So that's essentially what you do. That's essentially how this breaks down. You've got 3 multiples of this p to the 8th, then you can use the product rule. But the little shortcut the power of a power rule lets us take is we know we're going to have multiples of that same p to the 8th over and over and over again. How many? We're going to have 3 multiples, right? So in other words, the power of a power rule, says we have p to the 8 times 3, which is p to the 24th as well. So you can take that shortcut if you know it's going to be the same exponent over and over again because it's a power of a power, then just simply multiply the exponents. Do not confuse that with the product rule where you add the exponents. So it's power of a power, you've got one base, multiple powers, then you can multiply. Whereas in the product rule, you have a couple bases. Right here we had 3 instances of p times p times p, right? Multiple bases, you add them. Okay, multiple of the same base, but you add them together. Watch out for that. Alright, so that's the power of a power rule. Can be very useful in some situations, especially when you have things like p to the 8th to the 45th, right? You don't want to write out 45/8, so if you can use this little multiplication thing real fast, it'll be much faster. Let's talk about the distribution rule. Distribution rule happens in B. And it's exactly as you think it would work, right? Distribution. What do you think? If I've got 2 over 3, all of that to the 4th, then I can distribute that exponent. It works for multiplication and division. So multiplication, comma, division. It works for both of those. You cannot distribute to addition or subtraction because of that violates PEMDAS. But anything multiplication or division, you can distribute that rule or that exponent. So let's go ahead and do that. If I have 2 to the 3rd, or 2, excuse me, if I have 2/3 to the 4th, then I can distribute that as 2 to the 4th over 3 to the 4th. And I end up getting 16 over 81. Awesome. So I just distributed that in. Everybody got to play the game. So it goes to the top, it goes to the bottom. Same thing happens in C with multiplication. But this is where people trip up a lot. I don't know why, but just because you have a term just because you have a coefficient doesn't mean the coefficient gets left off. This is where that parentheses comes in again. Because the 3 is in parentheses, this is the same thing as 3 to the 5th, m to the 5th, okay? It is not 3m to the 5th. Do not be lazy. Just if you have the parentheses there, someone had to take the extra time to write those. Remember, mathematicians are lazy. So if they don't need to write parentheses, they're not going to. But if they need to write the parentheses, it means that they're there for a reason, right? They're there for a reason. Just like in this last problem. We needed to show that everything was to the 4th power. Here we need to show that everything is to the 5th power. And so we end up with, I don't even know what 3 to the 5th is. Let's see. That's 9, 27, 81, 243. 243 m to the 5th. Alright, and that's quite different than 3m to the 5th, right? That's a much bigger number. So watch out for that. That distribution rule is very important when it comes to parentheses. Let's look at them both together now, the power of a power rule and the distribution rule, and see what happens when we simplify this little guy. I encourage you to pause the video now, use both the power of the power rule and the distribution rule to simplify this fraction. Okay, so I hope you had a chance to I hope you had a chance to try this on your own. Let's start with that distribution rule, right? Because this 3 is on the outside of everything, therefore everybody gets a 3. 2 to the 3rd, m to the 5th to the 3rd, over z to the 3rd. Excuse me. Everybody gets a 3. Everybody. A couple of you are probably already kicking yourself because you didn't put the 3 on the 2, or maybe you forgot the z, whatever it is. But everybody gets a 3. Now we can simplify a little more. This first term here, we have to be super careful that that negative is not in the parentheses, so it stays on the outside when we cube it, and we get negative 8 over. Now we'll use the power of a power rule here. It says to multiply m to the 15th, and z cubed doesn't have anything else we can do, so we arrive at negative 8 m to the 15th over z cubed. And that pretty much shores out all of our rules. So we've got the power of a power rule, the distribution rule, we've got the quotient rule, back up here we've got the negative exponent rule, the zero exponent rule, and the product rule. Those are really the 6 you'll see when you need to simplify giant things like this. So we're going to use all 6 of them now in whatever order they may appear. If we use all 6, that's fabulous. If not, whatever. But we need to make sure we use, we can use anything we want to get down to the simplest form of this giant expression here. Now, on your test, on your quiz for this chapter, you may see teeny tiny things like this, but chances are when we hit chapter 5 unit test, this is all you're going to see. So being able to use all 6 at the same time is much more beneficial than being able to break them into individual pieces. So don't think you're going to have like a 400 question quiz. You're probably just going to be asked to use all 6 if necessary. All right. Use any of the above rules to simplify the expression so there are no negative exponents and only one of each base. That is how you know you have simplified enough, okay? If you have one of each base, one x, one y, and one z, then you are done. If you have 2 y's, there is still something you can do. I guarantee you. One of these rules will still apply if you have 2 y's. And if you have x to the negative 2, then you know you have more stuff to do because you're not supposed to have any negative exponents. So let's try this out. I'm going to rewrite this guy down here. Actually, let's start by we'll just work with this guy. Let's start with what rule? Let's start with that distribution rule because he's on the outside, right? So let's start with the distribution rule. Did you have to? No. But I don't like parentheses, so I'm going to get rid of it. I'm going to distribute everything. Everybody gets a 2, basically. Negative y to the 6 to the 2. Z to the 7 to the 2. X to the 4th to the 2. Y to the negative 2 to the 2. Notice I'm not actually computing anything. I'm literally just writing a whole bunch of 2's on the page. Z to the 0 to the 2. And then we'll go into the denominator. X to the 9th to the 2. Y to the 0 to the 2. Z to the 4th to the 2. X to the 2 to the 2. Alright. So everybody's got a 2. Fabulous. That's a whole bunch of distribution rule. Now I've got a whole bunch of power of a power rule. So let's go ahead and do that. So I'm going to do power of a power rule. Change all these guys. That first one is going to be, sorry, this negative is not in there. I shouldn't have drawn parentheses around that. The negative should have just been on the outside. Okay, so here we've got negative. Y to the 6th to the 2nd is going to end up being y to the 12th, right? Y to the 12th. Here we've got z to the 14th, x to the 8th, y to the negative 4th, z to the 0. All of that over. X to the 18th, y to the 0, z to the 8th, x to the 4th. So I just multiplied every single set of power to a power that I had. Alright, next I'm pretty much just going backwards now. I've got some quotient rule that I can take care of. I'm gonna take care of these zeros first. Anything to the 0 power, what happens? It turns into a 1, right? And if you multiply by 1, is that going to change anything? No, it's not going to change anything. So now if I ever see an instance of anything to the 0, I know that it cancels out. It cancels out. So what I'm left with is still a negative. Y to the 12th, z to the 14th, x to the 8th, y to the negative 4th, over x to the 18th, z to the 8th, x to the 4th. Alright, I'm going down. I see a negative in there that I can maybe get rid of, a negative exponent. So I'm going to change that negative exponent. I'm just going to move it to the bottom, right? Right, since it'll become, so y to the negative 4th is the same thing as 1 over y to the 4th, which will now go to the denominator. If the denominator is already there, then I can just move it down to the denominator. So I have y to the negative y to the 12th, z to the 14th, x to the 8th, over x to the 18th, z to the 14th, x to the 8th, y to the 4th. I'm sorry, not x to the 8th, y to the x to the 4th. Oops. X to the 4th. Alrighty. Now I can apply some quotient rule. I can apply some quotient rule and cancel some stuff. The z's to the 14th are going to cancel out. Let's use a different color. Z's to the 14th are going to cancel out. And they're left with none, which is awesome. If I have 8 x's on the top and 4 on the bottom, I'm left with 4 on the top. So I'm left with x to the 4th. And then for the y's, if I have 12 on the top and 4 on the bottom, I'm left with 8 on the top, right? Subtraction. So y to the 8th, pull that negative, and I still have that x to the 18th. All right, I've got one more thing I can do. I can cancel these x's using the quotient rule. So 4 will cancel, let's use red, 4 will cancel with 18 to leave me x to the 14th on the bottom. So I have my final product is negative 8y, or y to the negative y to the 8th over x to the 14th. Notice I have no negative exponents, a positive 8 and a positive 14, and I have one of each base, if that. All right, cool. Now, that is the way I usually see the problem done. So I usually see people tackle these in backwards order. They see the 2, they try to distribute, totally fine. That is a very extensive way. You're welcome to go that way. As you can see, you will arrive at an answer. However, you can use these in any order. So maybe you wanted to start by canceling the zeros in the problem. Maybe you wanted to start by doing all of the quotient rule, and that's totally fine. No matter what route you went, you probably would have got, or you definitely should have gotten the same thing. Okay, so no matter how you start with them, you should arrive at the same answer. Now, you must obey the rules individually, right? If you see a product rule, please make sure you're actually multiplying and you have the same base. If you see a 0, make sure you raise it, you cancel it out for a 1, right? Don't change it to a 0, okay? Make sure you follow all of the same rules, follow all the rules accurately, but you really can